Today we're going to be talking about translations, and they are important. They make it so we can graph a function quickly, efficiently, and accurately. Before we start with the rules, I'm going to go with the most basic parent function we see most often. And I'm going to start with a basic parabola. And there it is. Now, for this one example, I'm going to go ahead and use a table of values to show you the relationship between the x and the y values, because that'll make it easier to learn. And looking at the basic parabola, those are the points. If you don't remember how to generate these points, please see Graphing a Quadratic Function in one of my other YouTube videos, and that will go through that process for you. So there is our parent graph. When we are adding inside the function, it is a left motion a units. So in this case, it is left 2. So you take each point on the parent function and you move it left 2. This point, and now this point left 2. And you sketch the shape. If we are going to look at the table of values for the second or blue function, you will notice that the new translated function is, and notice what you're going to do, you're going to subtract 2 from the x values because that dictates horizontal motion. So if you subtract 2 from the x values, we get our new function. Accurate, you can see the shape and its orientation on the coordinate plane. This dictates vertical motion. So, looking here, this is going to be down 3. So we're going to take each point on the parent graph and we're going to move it down 3. So you can see how quick and efficient it is. Doing the table of values, this would subtract 3 from the y values. Hopefully you notice as you go up and down, you're only affecting the y values of the graph. So in this case, we start, notice, with the parent function, and if we subtract 3 from each y coordinate of the parent, we get our new function. Moving on, find my eraser. Oh, found it. Okay. So now moving on, let's do one more example. Actually, before we do the example, I want to quickly review. So this is your left and right, your horizontal motion, and you are adding or subtracting from the x values of the parent. This dictates vertical motion, and you are adding or subtracting from the y values of the parent graph. We will examine these two cases in just a moment. I want to do a few examples with the first 2 rules that we've established. So, for this next example, I'm going to go ahead and plot the parent graph so that you can see the net effect of your translation. Now, one thing I did not mention, these are what I like to call your reference points. Reference points are important because it gives you the shape and the location. So instead of doing a rough sketch that may be inaccurate, moving the reference points gives you an accurate graph. So if I gave you the function, let's do So looking at this, you are going to move each point right 2 and up 1. So you're going to take this reference point and you're going to go right 2 and up 1. You're going to take the next point, right 2, up 1. And you're going to take the last point, right 2, up 1. And then we're going to draw the shape. Notice it's nice and smooth, called parabola. And there we go. That is the translation. If you were asked to describe the translation, it would be right 2, up 1, or a horizontal shift, that is right 2, and a vertical shift, that's up 1. Going to, this eraser keeps disappearing on me. Oh, here it is on the floor now. Okay, so now I would like to get to reflections and steepness. Now, some teachers will do more translations that are more advanced, and that will be version 2 of this video. For now, we are just going to deal with these two. So the reflection about the x-axis, and again, I'm starting for comparison's sake. Okay, so for comparison's sake, I'm going to, what are these called? Reference points. So I'm going to start with the parent graph. And if I were to take, if there were a negative on the outside, that would be a reflection about the x-axis. So it would be as if you took the graph and you flipped it upside down. So instead of this point being 1 above the x-axis, it's 1 below the x-axis. Instead of this reference point being 1 above the x-axis, it's 1 below the x-axis. And if you're on the x-axis, you stay there because you are not above or below, you are on. And we're going to draw a nice shape, and that would be the resulting graph. So notice here is the parent graph and the translated function. If I were to have a coefficient on the front or on the outside, let's say, actually let's start a new graph so I can get this. And why don't we're going to do 3 graphs again on one plane. Notice the color of the pen corresponds to which function I'm graphing. And that makes it easy. How many of you have been in class, you understand it, you go home, and it's left your mind? So color coding is one incredibly efficient way for you to trace your thinking so that later, when you come back to a problem, you have the ability to figure out what the heck you did. So here, we're going to start with our parent function, and we are going to plot our reference points. So if I gave a function such as, I don't know, why don't we do 2x squared? This means the graph is twice as steep. The different teachers use different languages, the words to say this. It can be a vertical stretch by a factor of 2. You could say twice as steep. So instead of going up 1, you're going up 2. And you're going left, instead of up 1, you're going up 2. And notice if we were to create a table of values, as we did in the previous example, notice these are from the parent function, the reference points, and we were to, those are the points, and just plug it in the good old-fashioned way. So if you plugged in negative 1 squared is 1, 2 times 1 is 2. 0. 0 squared is 0, 2 times 0, 0. And 1. 1 squared is 1, 2 times 1 is 2. So you notice here, you are affecting the y values, making them twice as steep. So looking at the parent graph, if you know the parent graph's y coordinate is 1, 2 times 1 is 2. As opposed to if I did, that's going to be half as steep, or a vertical stretch by a factor of a half. So you're going to take your, remember, the y values are not affected in this case, and you're going to multiply 1 by, there's a half as steep. So instead of going right 1 up 1 as we do on the parent, you're going to go right 1 up a half, left 1 up a half. And notice, it's hugging, it's much closer to the x-axis. So now we're going to move on and we're going to do a couple other parent graphs. For the parent graphs, the first one I'm going to do is absolute value. And those reference points are 0, 0, 1, 1, negative 1, 1. They happen to be identical to the parabola. The difference is the shape of the graph. It is a nice V. So if I gave you a translation, why don't we do a y equals negative x, plus 2. So if I were asked to describe the translation, it would be up to reflection about the x-axis. And it's always helpful to do the reflection first. So if you were to reflect this, notice you would have it upside down, and then you're going to move each point up 2. So instead of being 1 below the x-axis from the reflection, you are, right here. There we go. Notice it is flipped and up 2. If I had it this is going to be horizontal motion to the left 4, up 2. So the coordinate plane isn't quite big enough. So you're going to take the vertex and you're going to go left 4, up 2. You're going to take this point, left 4, up 2, and the same with the last point. Left 4, up 2. Remember, absolute value is always a nice V. If our parent graph were absolute value, square root of x. That parent graph looks like 0, 0, 1, 1. And those are your reference points, 0, 0, 1, 1. Why don't we make this 3 times as steep? So instead of going right 1, up 1, you're going to go right 1, up 3. Notice 0 times 3 is 0, so the start point doesn't move. Let's say I did something like that's going to be left 1, down 3. So from the reference points, left 1, down 3, left 1, down 3, a nice smooth curve. Now we're going to go on to another parent graph that's quite common, and that's going to be a cubic function. So for a cubic function, give me a little more room here. These are the reference points, and the shape is a nice smooth curve up, a nice smooth curve down. So if I asked you, say, to That would be horizontal translation left 3. So you're going to take each reference point and you're going to move it left 3. If I said, why don't we do negative x to the third, that's a reflection about the x-axis. So if you took this graph and you'd rotated it, you're going to get this resulting graph. I'll go ahead and make that dotted. It's a little easier to see. And you can see it's as if you flip this upside down, which is what a reflection about the x-axis would be. Okay, the last two translations at times you see is a circle and an ellipse. We'll start with the circle. Actually, we're going to, it's not necessarily helpful to think of circles and ellipses as having a parent function. There's a lot of variation in how it's done, and that's going to equal, I don't know, why don't we let it equal 4? So hopefully you remember, this is going to be right 1, down 1 for the center. So our new center is going to be 1, negative 1. So notice 1, negative 1, that's our center, as opposed to the parent graph would have a center at 0, 0. And then we take this number, whatever it is, and we take the square root, and we go from the center, right 2, up 2, left 2, down 2, and you make a nice circle. If I gave you something like x plus 3 squared plus y squared is 1, that's going to be a center at negative 3, 0, and the radius is 1. So you're going to go to negative 3, 0, and you're going to go right 1, up 1, down 1, left 1, because that's a radius, the point from the center to the edge of the circle. You're going to draw a nice smooth curve. Okay, moving on to the ellipse. I'm going to start with something like no, let's do minus. Okay, so there's the form an ellipse takes. And the center here is going to be similar to the circle. So the center in this case is 2, negative 2. Notice it's opposite to sign, and that's because of the way we define the initial function, which will be in my conic section video. And here you take the square root of 4, which is 2, and because it's under the x, which is right and left direction, or horizontal motion, you're going to go right and left 2 from the center. And for your horizontal motion, you're going to take the square root. Notice the 16's under the y. The y direction is vertical, up and down. So you're going to go up and down 4 from the center. So we're going here, nice coordinate plane, and you're going to go to 2, negative 2, that's your center. In the x direction, square root of 4 is 2, as we said, right 2, left 2. And in the up and down direction, we're going to go up 4 and down 4. And there's our ellipse. Mine's a little wonky, but you get the idea. And that is translations.